is, first of all, these aren't just over increasing sets of I1 through IP, right? That's just, it's got everything there, but there's a bunch of zeros in there, right? Anytime like I1 and I whatever are equal, then this works out to be 0. Anytime you have the wedge product of two things that are the same thing, like dual vectors that are the same thing, necessarily 0. So what happens here is it's basically, you see the p factorial, right? So it's just essentially a combinatorial thing. Like I can rewrite this is equal to that. I just let I range from 1 to n rather than looking at distinct ones. So there's a short notation for this. The short notation for this is, let me get rid of this mess. And my apologies, Ernesto, if I'm not making too much sense today. I'm trying, but this stuff is hard, honestly, to communicate decently. I will eventually figure out how, but I always have a hard time with this particular part of the material. Anyway, so this we can write as the sum over the multi-index I in IP, and then I've got T sub I E upper I, all right? Whereas this up here is simply the sum over I of 1 over P factorial T sub I E upper I. So this is just like, you know, there I'm just taking arbitrary, so this is just like over arbitrary, you know, length p indices from 1 to da 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 n. Whereas this I sub p, this is the set of increasing length p indices from 1 n. So there's tons of things that are 0 in the one that doesn't use the increasing indices, but it's very freeing because you don't have to use indices, increasing indices. The bad thing is that is not a basis expansion, whereas this is a basis expansion, because you can prove that these things with increasing indices form a basis for the p forms over lambda v. Whereas here, because you have things like, for instance, if I'm just make p equal to 3 for a second, I will have the case that p123 is equal to minus t213. So because those are intertwined, if I have a summation that involves both, I can't conclude anything from one of them being 0 unless I'm enforcing, unless I also know that this is enforced. You know, if I know that my indices are antisymmetric, then fine, but before the fact in certain calculations you don't know that, you're trying to prove it. So that's why that is dangerous. Are we good? All right. So now that we have all this, we can define the wedge product. So, and it's defined as follows. And we'll define it using the basis expansion as to keep ourselves out of trouble. All right? So suppose you have, we should use alpha and beta here. If I have alpha in, let's say it's a P form over V, and beta, let's say, is a Q form over V. So that means that we can write alpha as the sum over alpha I, E upper I in increasing P, and beta as the sum over J in Q indices of beta J, E upper J. Then alpha wedge beta is equal to, oh man, did I, son of a gun. Look at that. Oh, fine, I did what I did. This stink. Well, I got bad news. I actually didn't do that. I did the 1 over P factorial, and I did the 1 over Q factorial here, way of thinking. And so, you know what? It's just what you'd kind of expect. It's the sum over I, the sum over J, 1 over P factorial times Q factorial, alpha I, beta J, EI, wedge EJ. And why is that a reasonable definition? Well, that's debatable, I suppose, but it's a definition. I think it's somewhat logical, given our lead up to this, because we've already defined, well, the question is, how do you define the wedge product of two things like this, right? Like, what does EI wedge EJ mean? We're talking about like EI1 wedge wedge EIP, right? Wedged with what? With EJ1 wedged wedged with, oh good grief, my wedge has gone up into my index. That's not good. Wedged EJQ. And the definition of this, which I have not made yet, I suppose, but it's what you'd expect. It's EI1 wedge EIP wedge EJ1 wedge EJQ. So we're basically imposing associativity at the level of the wedge product of the dual vectors. That will bequeath associativity at higher levels of this construction. The wedge product will be associative. And of course this we could define as what? Like, this is the sum over sigma in what? Like, it's apparently P plus Q permutations, right? And it would be E I sigma of 1 tensor E I sigma of P tensor E I J sigma, J, dummy, of sigma of P plus 1 tensor, I think this is what it would be, right? I could be wrong. Probably should think about that. P plus Q. Well, anyway, I think that's what this has to mean, right? Yeah. Technically, in order to apply my definition, I need to re-enumerate this, right? Technically, I should re-enumerate this with like EK1, KP, KP plus 1. You know, I need like KI equal, oh, good grief. K sub L equal to I sub L. L equals 1, 2, P. And then I should think about K sub L is equal to J sub L for L equals to P plus 1 da 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 P plus Q. So then I would have a wedge product of dual vectors enumerated by a single index, P plus Q index K, and then I can apply my definition and I would get this. It's the completely anti-symmetrized tensor product of P plus Q dual vectors. And of course, this does beg a question in some sense because it's not over, like this isn't over a basis, but it nevertheless is a good definition. You could rewrite this as just the sum over I and IP, J and JQ. I mean, let me do that. Another way to write this, and I'm not going to prove that this is true. It's true though. So IP, sum over J and IQ, that drops this out. And then we've just got increasing indices. But now we have to extend the meaning, actually, of something like this. I usually write epsilon I, J, and then E, I, J. Where this E, I, J is either equal to I don't know if I usually define this or not, but oh, I'm a dummy. Let's define it this way. E K1 wedge E K2 wedge da 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 wedge E KP plus Q, where K1 K2 da 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 KP plus Q is equal to, using multi-sets, I allow repeats. Multi-sets. Who knew you needed them? I2, da da IP, J1, da 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 JQ. So this is that set, the same set of indices, and K1 less than or equal to K2 less than or equal to K3 less than or equal to da 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 less than or equal to KP plus Q. And this is equal to epsilon IJ EI wedge EJ. And what that means is that epsilon IJ is either equal to plus or minus 1 if I intersect J is empty, and it's equal to 0 if I intersect J is non-empty. If there's any repeated index between those, it's 0. 0. Yes. That is the definition of the wedge product of p-forms. Es bueno? Y bueno. There is doubtless a more efficient way of defining this. I think this was the point in advanced calculus that I taught a couple of years ago, where it drove me to look at a book by Jeffrey Lee. Jeffrey Lee has like a very, very complete and pretty solid definition for the wedge product in terms of anti-symmetrized tensor product, but it is a lengthy and somewhat technical definition, but it's also not an abstract algebraic one. It's very much in the flavor of what we're doing. So, all right. But now that we've gone through all this trouble, we should appreciate we should reap some of the fruits of our labor before we stop this week. Otherwise, we'll regret our life. We don't want to do that. So, what can we say about all this? So if you look at this formula, I mean, there's some questions that are begged here, right? Because it's made in terms of a basis. So from a linear algebraic perspective, it's like, how do you know this isn't basis dependent? That's one annoying question you could ask. Let's not ask that question. Turns out it's okay in that regard. Like, it's consistent. If you used a different basis, you'd get the same thing. I can kind of sketch that. The reason for that is if you change basis, the components and the basis, the dual basis, they transform inversely. And so it's still the same thing in a nutshell. The other thing is, if I write this, I am assuming that these components have antisymmetry. So like there's no ambiguity in the expansion. All right. All right, so setting aside concerns we might have about whether or not this definition is completely on the level, what would properties of the wedge product be from this? Can you see any? What are the properties of the wedge product? Would it be commutative? Is an interesting question. It would definitely. How about this? If I had like alpha 1 plus alpha 2 wedge beta, I think you can pretty easily see that would be. I mean, instead of alpha 1 and alpha 2, let me use like gamma, alpha and gamma, right? I think you can see that would be like alpha wedge beta plus gamma wedge beta from this formula, because you just replace alpha with like alpha plus gamma, and the components of alpha plus gamma would be like alpha sub I plus gamma sub I, and when you like put it here, because this is the product of real numbers, it's distributive, and then the sums are distributive, and yay. And it's also going to be true that it's, if I had, like delta plus beta, you'd also have this kind of linearity as well, right? And I think it's also fairly evident that we can pull constants out, right? Like if I had a constant here, I can pull it out. If I have a constant here, I can pull it out, And you can pull it out of the first one as well. So it's additive. It's homogeneous in the sense we can pull constants out. Is it commutative, though? That's an interesting question. That's a very interesting question. What if we have beta wedge alpha? That would give us the sum for what? I sum over j, right? And I'm actually going to go ahead and use this formulation. So we'd have beta, oh man. Let me start with alpha. Let me start with what we have. So alpha sub I, beta sub j, epsilon ij. So it's kind of funny if you think about it, but I believe that I don't know if I'm going to see it at this notation. I'm not sure I can make it convincing. So this is supposed to be like rearranging them so they're in increasing order, right? So for a fixed choice of I and j, it would be the same. So this is actually, so you agree that it's clear that this is equal to that E ij would be equal to E ji. Yeah, I think that's got to be true. Okay, so And also, let me just go ahead and flip the sums. We can do that. They're finite sums, but well, there's many of them, but we can flip their order. That's a theorem. And yeah, we can flip these as well. That's just real number multiplication. And we've got our epsilon ij, whatever that is. And we've got our eji here, right?
And epsilon ij, we can flip this.
That's the question, is can we flip the epsilon ij?
Well, but I intersection j is the same as j intersection I.
That is true. So it's going to, okay, so granted. So let's think about this now. Let's think hard about that. Because you see what we need to do. We need to trade that. Once we have this as epsilon ji, right? Then by definition, this would be beta wedge alpha.
Yeah.
But it turns out that these are not equal. They are definitely equal when I and j, as you said, don't intersect. Excuse me, when their intersection is non-empty. Because they both have a repeated index. They're both 0. 0 equals 0. However, the plus or minus 1 is going to flip around. I didn't really define this carefully enough yet, did I? So let's see here. Maybe you can see it up here. So if I had epsilon ji, right, it would be equal to, you know, epsilon ji, right, times ej wedge ei, right? But how do I change this to that? And again, we're in the I'm in the I'm assuming that they're distinct. I and j are distinct indices in the current consideration. Well, that means that I have to move each one of these past the j. It might help for me to actually write it out in this kind of notation. Let me erase that up there. We're done with that.
Kind of like what? Super number?
Yeah, it's a lot, very much like supernumbers. Oh yes, very, very relevant. If I was more on my game, we would have just used supernumbers. Probably could have used supernumbers to define this stuff if I was really with it, you know?
Because the wedge product is making an algebra with the lambda b.
Yeah, I do think it's the same math. So this right here is explicitly ej1 wedge wedge e. How many? I think q, right?
Yeah.
And then we've got I1 wedge EIP. So to move this to the front, I have to flip-flop q-fold times. So I've got minus 1 to the q EI1 wedge, I'll just write it EJ, okay? Wedge EI2 wedge EIP. And then you see I have to do that one past the EJ. And so I get a minus 1 q, minus 1 to the q, EI1 wedge EI2, wedge EJ, wedge EI3, wedge EIP. Okay, so this continues until we eventually have minus 1 to the q, minus 1 to the q, EI, wedge EJ. How many of these do I have? Well, I have as many indices as I have, and I have as many of these as I have indices. There are yeah, p-fold of those, exactly. And so what do I have? I have minus 1 to the,
B plus k.
well, q plus q plus q plus q plus q plus q, p. Yeah, pq, exactly. So it's beautiful. This is actually minus 1 to the pq times the other one. And you see we have minus 1 to the pq beta wedge alpha. So they don't commute. They there's a graded commutation relation. So it's -1 to the degree of alpha times the degree of beta wedge alpha. So what this means is that the wedge product of two things is not automatically, excuse me, the wedge product of a P form with itself is not automatically 0. Notice that when we have an even degree form, like if I have a 2 form, so like if this is 2 and that's 2, I'd have -1 to the 4, right? Now if you have the wedge product of an odd form with itself, then that has to be 0. But we can have like a 2 form wedge itself be non-zero, and that matters. If every so often, you got to watch out for this. I'll be careless and I'll just say a wedge product of a form with itself is 0. When I say that, I'm thinking one form. I've just omitted the one form. Wedge product of one forms with itself is 0. But anyway, so yeah, that's the next interesting. It's not commutative, but almost commutative. And the other deeper thing, which I don't want to prove, but I do want to claim, is that this wedge product is associative, yes. So that's also true. And then, so we'll continue talking about this next week. We'll build this up to the whole exterior algebra, and then we'll see there's so much more to appreciate here. So.